until I'm on it all day, run out for tomorrow. Figure it out.
Good evening. Happy Monday. Exams are graded, as you no doubt know. Solutions are posted, just like with the quizzes. Went about what was expected. Average was a 60. There's only also 8 of you, so that's to be expected. Average gets hit a lot more. I said this is the hardest exam. Techniques of integration is the hardest. So don't fret. We do have the midterm coming up in, 4 weeks? 3 weeks? How's the coding going?
We're working on it.
It's easy, right? Already done. Let's extend it to the 4th. Give you an extra weekend to work on it.
Oh, good. Okay.
I was thinking about it this weekend. So let's extend that out to be on the 4th, and you should receive a notification on the assignment change on Teams as well.
Okay.
If you don't receive one, let's say by midday tomorrow, someone message me and remind me to extend it. So this lesson got a little technical. And you can expect that for pretty much the rest of the applications. It's going to be very theory heavy in the videos. Right? Because we're deriving these techniques. So our first question that we ask is, we want volume. How can we find it? Well, of course, you have your formulas from geometry. Right? So you have geometric arguments. Right? I believe that you're introduced to geometric arguments for several volumes: sphere, cone, cube, a rectangular object, right? 3-dimensional rectangular box. I believe they were all given geometrically. We look at it analytically, right? Calculus-based. Could be either dx or dy, depending on the variable that you want to define. But this is what we came up with. This is what was derived. It's the integral of a cross-sectional area. The integral is the easy part. It's generally finding the cross-sectional area that's a pain. So this is known as the method of slicing for finding volumes. And this method is what's used to derive the disk method that we study. I think it's on Wednesday we look at it. I guess I'll actually. So, volume of a sphere of radius r centered at the origin. We know what that volume should be from geometry. What should the volume be? Uh-oh. Volume of a sphere, we don't remember. That's not good. It's one of the basic volumes.
Something like pi r squared.
That's area.
That's the area, okay. Is it pi r cubed, maybe?
Close. Well, I guess we're going to do the calculus and find out. So the idea of slicing, and we're going to pretend that's a sphere. So we take a cross section of it. Cross section of a sphere is a circle. The circle is going to have radius little r. Right? The radius of the cross section is solely dependent on where on the sphere you're taking the cross section, right? If you take the cross section here, obviously the radius is going to be smaller than if you take the cross section right in the center. I'm going to draw my XY axes. So we're going to say that the center of this cross-section circle is some point on the x-axis. We're going to call that point x. Right. Call that y. And obviously we have some length there. I actually know what that length is. That has to be radius of the sphere. We need to find a formula for the area of that cross section. Well, we know what little y has to be. Wait, no, we don't. Not yet. Yeah, we do. Little y is this little r. That doesn't really matter. X squared plus y squared has to equal big R squared. We know that. We can solve for either x or y. Well, because of how we have it drawn, it'd be better to solve for y, right? Because little y is the radius of our cross-sectional circle. Y squared have to be r squared minus x squared, big R squared minus x squared. I'm actually going to leave it squared. Area of a circle is what?
Pi r squared.
But in this case, our radius of the circle little r is y. There's our area. We need limits of integration. So what we do is we look at this. Here we go. This center right here, right? Because that's how we're taking the cross-sectional area. It slides along the x-axis inside the sphere. So what are our bounds for x? Now, what is the smallest value x can take on?
Minus r.
And what's the largest value?
R.
There's the volume, which has to be evaluated. Well, that pi is constant. Well, big R squared is a constant, right? Antiderivative of x squared x cubed over 3. R minus negative r is 2r. r cubed minus negative r cubed would be r cubed plus r cubed. And then 2 minus 2/3
4/3.
4/3 pi r cubed. Which, if you remember the geometry, that's the volume of the sphere.
Is it just that, or is it the integral of that?
I mean, this is this evaluated. Right, so this is the volume.
Okay.
This is what we evaluated to get the volume. So they're technically all equal, they're the same. They all mean the same thing.
Okay. So in the end, can we really do this just by knowing what big R is without knowing the rest of it? If we knew what big R was,
Yeah.
that all the problems we had will have us make us have to find the big R.
No,
No?
this was a derivation.
Oh, okay.
So this was just to show you that geometry is correct.
Okay.
We're assuming that's what your geometry teacher told you. Geometry is correct. Right circular cone has height h and base with radius r. You'll learn in Calc 3 that a cone itself has a specific definition. And the cone that you're most used to is called a right circular cone. It's just a special cone. In general, cones do not look like that. So like an upside down ice cream cone looks like. So it has a height h. And the radius of the base is little r. Cross section is again circular. Now comes the fun part. So here's what I'm going to do. Let's call that radius x. Right, so if you imagine where I drew the height, imagine that as the y-axis. And we're centering all of our cross sections on that y-axis. that will have y, and then that's something. Well, by the way, if I draw the radius like this instead, that's still a little r, right? We have similar triangles. That triangle is similar to the smaller orange triangle. The area of that circle is going to be pi x squared. We just need to find x in terms of y. Bisimilar triangles. Ratio of the base to the height of 1 has to equal the ratio of the base to the height of the second. So x over y has to equal r over h. So that should be ry over h. Now remember, little r and little h are constants. They're known, right? The height of the cone is going to be known, and it's unchanging. The radius of its base is going to be known and unchanging. So the only values changing here are the x and the y based on where we're taking the cross section. So volume is the integral of this cross section. Pi x squared. X squared is r squared over h squared times y squared. Then we're integrating that with respect to y. Limits of integration. So again, you have to imagine the center of your cross section here up to here. So what is that lower limit?
R. H.
And do y or y.
Y is what we're integrating with respect to. Kind of a trick question. You can actually set it to whatever you want it to be. Why don't I take the base as being on the x-axis? That would make our lower limit for y 0. Then what's the upper limit? So it comes up to here. What's that upper limit? What does y equal up there? H. 0 to h. Even if I flip this around and make it a right side up ice cream cone, I can still use the same arguments. Set the bottom still as the x-axis and go 0 to h. All my arguments are going to be exactly the same. I could set this as my x-axis. Then we go negative h to 0. Everything's going to work out the same. You could set that as 8. You go 8 to h plus 8. This is just the easiest setup.
So it's really h plus the
yeah.
H plus.
Right, because whatever this value is, the cone has height h, right? So at the top, it's going to be whatever that initial value is plus the height of the cone. Now I just have to evaluate that, right? Well, pi r squared over h squared is a constant. So we can factor it out. Oh, and that's a really simple integral to evaluate, isn't it?
Yeah.
Antiderivative. Y cubed over 3. Evaluate that from 0 to h, you just get h cubed over 3. One third pi r squared h. Which is what geometry gave us. Once again, geometry is proven correct. Right, so we're going to find the volume of this pyramid. Let's see. That's better. Good enough for government work. I don't think that was supposed to be quite straight. Well, whatever. Doesn't matter.
Does a pyramid mean the bottom is a square?
This one is.
Okay.
Pyramid doesn't have to be square base.
Okay.
That's 2. We're gonna have height 6, which I actually had that as straight, so I'm just gonna call that my height 6. Yes, I can, okay. All right, okay, yeah, they did this. That's fine. That's height 6. Base is a square of length 2. Cross section. Is going to be a square. Let's say that side is length x. And it occurs at some height y. Or a triangle. That's not the triangle I draw. There's one triangle. Which right now I will cover this in white. There's the second. Similar triangles. Area of that square is going to be what? X squared, right?
Yeah.
We need to write x in terms of y. Right? Because x, that length, depends on the height that we take across the section. So it depends on y. Well, once again, by similar triangles, x to y equals what?
2 to 2?
Except that should not be y.
Oh.
I'll deal with that later. Base to height. That's not y. Right? Because the height I'm looking at is this height here.
6 minus y.
X to 6 minus y is 2 to 6. And of course, 2 to 6 is the same as 1 over 3. X would be a third 6 minus y. Volume. Integral of that cross-sectional area. 1/9. Quantity of 6 minus y squared dy. Lower limit of integration.
Zero.
Set it as 0. What's the upper limit going to be?
6.
Integrating 0 to 6. Right? How would you evaluate that?
Just plug in.
Well, maybe you need an antiderivative first.
Well, first I think we probably got to expand that out.
You can do that.
Yeah.
There's a simpler way. Let 6 minus y be u. What's du?
2u.
It's 6 minus y quantity squared, right? So I'm just saying u is 6 minus y.
Oh, du is 2y, right? 2u, I mean, no. No.
So what's the derivative of 6 minus y?
Oh, the derivative of 6 minus y is probably just 1. Negative 1.
It's negative 1.
Yeah.
So my answer is multiplied by minus. U cubed over 3. There's our antiderivative. At 6, you get 0. Minus negative 1/27. 6 cubed. It's 216. However, will that make it easier? Probably. Because six cubed is 2 cubed times 3 cubed, and 27 is 3 cubed. Look at that. You're left with 2 cubed, which is 8.
Yeah.
So 216 over 27 is 8. So this pyramid has a volume of 8 cubic units. Good enough government work. Actually, that should be like this. Something like that, yeah. Then across like that. That's right. So this height here is a height of 4. It's not a square base anymore. So let's look at this. Cross section is going to be rectangular. Let's call that L. Let's call that omega. Or curly W. And by the way, this actually has a script. Coding ELL. L. Oh boy. Let's go with oh wait, oh my god, I need a 4th color. Let's go with you. Area of our cross section. L times omega. So let's say that we drew this cross section at a height y. So everything is dependent on our height y. So we need to find a formula for L in terms of y and a formula for omega in terms of y. Let's start. So you clearly have that yellow triangle. And we also have that purple. The yellow and the purple are similar. Base to height is equal to base to height. So look at the larger one, the yellow. What's the base?
3, 32.
What's the height?
4.
3 to 4 has to equal the purple. What's the base?
2W? L?
I'm sorry, what is for the height?
It was given.
But it's not in the triangle, no?
Doesn't have to be, that's the height of that triangle. Right, because the whole pyramid has a height of, right, so you have to remember this is 3D.
Okay.
So this height is flat, so it's actually on this line.
So like it's not gonna be the hypotenuse if you connect the height and to the height.
Well, you could try and draw a right triangle.
But it's still gonna be like 4?
In this case, the height would be 48. Right, so again, you have to imagine this is actually, I'm trying to draw this popping out, but it's flat, so the height is, technically, that's the base right there.
And
So this 4 goes from here to the tip. That's the yellow triangle.
What part is W?
It's the whole thing.
Okay, so W would be the base then, right? The
Yes.
little triangle, all right. And then what was Y?
What is the height? Y is variable. The height varies.
I mean, on the picture though, like,
Y is this orange. So it's from the base, essentially from the base to the base.
so then the bottom would be 4 minus Y.
Yes.
Yeah.
Alright, so if you imagine that's my cross section, this is the base of the rectangle, Y is that height.
Okay.
This will allow us to solve for omega. Okay. There's a green triangle. The height would be the same, by the way, based on how the pyramid is. What's the base?
2.
But then we also have that red one. The red and the green are similar. What is the base?
L.
And what is the height?
I think it's still 4 minus Y.
It's the same. Which means that L is 1/2 of 4 minus Y. Our cross-sectional area (3/8) the quantity of 4 minus Y squared. Right? It's L times omega. Limits for integration. There's the volume. Now we just have to evaluate it. Oh, well, that looks very similar.
Yeah.
Just do U sub with U being 4 minus Y. You'll get 1/8 the quantity 4 minus Y cubed from 0 to 4. At 4, it's 0 minus negative. So we get something over 8. It's 4 cubed over 8. Well, 8 is 2 cubed. 4 is 2 squared, right? So 4 cubed would be 2 to the 6th. 2 to the 6th over 2 cubed is 2 cubed. Volume of this also happens to be 8 cubic units. That is the slicing method. This assignment number, I think it's number 10, 9. Looks like number 9. It's probably going to be one of the harder homework assignments because it's a bunch of slicing method. And you have to try and find the cross section. So this one's probably going to be a little challenging. Are there questions on slicing method?
You would have to come up with a new formula for every problem?
Yes.
Okay.
The idea is the same all the time, right? You find a cross section, and you determine where that cross section is. Is it going to be based on y height or x this way, right? So for the sphere, I could have done either one. I chose to do it vertically. So it's depending on x. All of these we've done horizontally cross sections, right? Horizontal cross section. So it depends on height y.
Okay.
Then the idea is now you have to find area in terms of what's changing, the x or the y.
Okay.
Yeah, assignment 9. It's going to have a bunch of these volumes. It's going to have densities. And it's also going to have what we're going to look at next, average value. All right, so watch the video for densities. Very similar to an integral. All right, so mass density, total mass is the integral of the mass density function. Then you have population density, which is radial. I think there's electric charge density, which is the same thing.
Where's the video?
On Teams, under classwork.
Okay. Class materials.
Classwork.
Oh.
And this is week 5. So you just open up the week 5 module.
Oh, okay.
And then there's the video, the lecture video. And then tomorrow will be tonight's recording.
Okay.
This was newly added since the summer course,
Oh, okay.
the classwork section. So it's very much like Blackboard, sets it up as modules. I really like it.
Okay.
So everything is like right here listed out on when we cover it. You can't see week 6 yet. I won't make that available till
So we
tomorrow.
actually do include that.
week 6 starts tomorrow,
Oh,
technically. So I'll make that available tomorrow morning so you can see 1 through 5, but everything's there.
okay.
You also can just go to my YouTube channel and they're there. And also, I think your textbook does a pretty good derivation of these densities as well, I believe. I actually don't remember if it does density or not. I know it does volume by slicing. It's the first half of the disk method section. Okay. So let's go back to statistics. I give you a data set. You have n data points. What's the mean? What's the average value?
I'll add it up and then divide it by the number.
So it'll be 1 over n. Summation I equals 1 to big N. You have x sub I, right? You add up all the data points, divide by however many there are. So when we talk about average value of a function over an interval, bless you.
Thank you.
Don't hold them in, it's actually very dangerous.
I didn't. I just,
That's
you don't want to
your
come out all the way. You just
That-
like stop midway.
Well, that's also dangerous. So you have some function, right? From A to B. So really, we're looking at all of these function values, right? What's its average value?
How many of them are there?
That's the problem, isn't it?
Yeah.
How many points are there?
I mean, I don't see. Well, there's an infinite number.
Yes. There's an infinite number of values.
Yeah.
So how can we find the average value? So glad you asked. Derivation's in the video, but recognize if we just break it up into points, this is what we get. That's a Riemann sum. So using that idea, and again, I'm not going to go through the entire derivation on the video. Very important. Your function has to be continuous on the interval to have an average value. So average value, we denote F bar. And I also sometimes include this to signify it's the average value over this specific interval. I could also do this instead of a subscript. So average value of f over a to b, 1 over b minus a times the integral from a to b, f of x dx. So we're going to find some average values. One over the length of the interval. And b minus a, 3 minus negative 1. Integrate from a to b, f of x dx.
Oh, I didn't even see that last one.
We get a quarter. How do we handle this? It's not equals. So what is the antiderivative of absolute value of x?
I mean, is it just 1/2 x squared? Is it either that or negative 1/2 over?
It depends, doesn't it?
Yeah.
Depends on whether x itself is positive or negative.
But it would be either 1/2.
It's going to have to be either x squared over 2 or negative x squared over 2.
Yeah.
Again, depending on the value of x itself. Well, x isn't strictly positive or negative over this interval, is it?
Is this going to turn into like a piecewise?
Well, it's not going to be piecewise.
Okay.
Integrals cannot be piecewise. Remember, integrals is some value is a constant.
Okay.
The antiderivative is piecewise, I agree. But an integral itself can never be piecewise, it's a constant.
Oh, okay.
Well, x is negative from -1 to 0, right?
Yeah.
Absolute value of x would then become negative x, right? And that's positive from 0 to 3. Absolute value of x then just becomes positive x. So I have to split this into two integrals.
Kind of like if it's discontinuous.
Yes and no.
Okay.
Because the absolute value of x itself is a piecewise function.
Mm-hmm.
So we have to split it up at the break of the interval.
Yeah.
Right? Because remember, absolute value of x is that?
Yeah.
So we have to break the integral up at 0.
Mhm.
It's not discontinuous at 0,
We just have the percentage.
right? Because the absolute value of x happens to be continuous.
Right.
So it's not discontinuous at 0, but the function itself breaks
Right.
at 0.
Okay.
Notice I can factor a negative out of here, right? So I'm going to write that second as a minus. Antiderivative here. X squared over 2 minus x. We're going to evaluate that from, not 1, from 0 to 3. Minus x squared over 2 plus x. I don't want to do this. That goes from minus 1 to 0. And don't be like me and forget the 1/4, because I always forget the 1 over b minus a. I don't know why. 9 halves minus 0 is just 9 halves. Three minus 0 is 3. Zero minus a half. Negative 1 squared is still positive 1. Then we get minus 0 minus negative 1. Nine halves plus half is 5. Minus 3 is 2. Minus 1 is 1. Average value is a quarter. Who remembers the mean value theorem from Calculus 1?
The integrals, right?
Not mean value theorem for integrals,
Oh,
just mean value theorem.
one for derivatives and one for integrals.
You shouldn't have gotten one from, you shouldn't have gotten one for integrals. From Calc 1, that's a Calc 2 topic.
This.
I actually should do a proper interval. of x is continuous on your interval, then there's some point in that interval, call it c, such that f prime of c, f of b minus f of a over b minus a. In other words, there's a point in your interval where the instantaneous rate of change equals your average rate of change. Right? If you go on a road trip and your average velocity was 60 miles per hour, the only way that's possible is if at some points you're under 60, at other points you were over 60, right? Which means there has to be at least one time in your journey that you were doing exactly 60 miles per hour. Right? The only way to go from under to over is to actually pass through that point.
Right.
That's what this is saying.
Okay.
There's a mean value theorem for integrals as well. So once again, f of x is continuous on our interval a to b. Then there's at least one point c in your interval, such that f of c is 1 over b minus a times the integral from a to b of f of x dx. In other words, you have a continuous function. There has to be at least one point where your function evaluates to the average value of the function over the interval.
He said it one more time, please. Can you repeat it?
So if f is continuous over an interval, there has to be at least one point where the function is your average value. That's guaranteed. But does that work if you're just given a finite data set? Does one of your points have to be the average value?
Not necessarily.
No. So why the difference?
Well, because if they give you a finite, I guess a finite range, right? If they give you a finite range, it might not necessarily go through that point.
Right, that's the difference, because you're dealing discrete versus continuous.
Yeah.
Finite versus infinite. And again, only works if f is continuous. Right, again, another thing this is saying is your average value actually has to fall on this line somewhere. Right? It can't be like here. That's not possible. Right? Your average value is going to lie somewhere on that line. Has to. Let's say it's there. That's F of C. That would be C. Now, it's possible there's more than one point where it's true. Notice what these two theorems don't tell you. There's two things they don't tell you. First, they don't tell you how many points it happens at. Right? All it's saying is it's guaranteeing there is going to be a point where it happens. It doesn't tell you how to find that point. Right? It doesn't tell you what that point is. It just says it exists. A lot of theorems in mathematics is like that. They just tell you it's guaranteed to exist. And then someone asks, okay, well, what is it? We just go, don't know. We just know it exists. Keep your eyes peeled on the schedule because you're probably going to get another assignment added. I found a very interesting news article on mathematics and the idea of sequences. I actually forget what the name is called right now, but it has to do with sequences. It's actually a really interesting article. So I may make you read that article and write something on it. Good news is it's just a news article. It's not math jargon heavy. It's not the actual math paper itself. It's just an article on the paper. If you were an honors class, I'd probably actually go and try and find that article and make you read the actual math article. Ooh, this one's nice. So it's what, 0 to 2 pi? Perfect, we have a power outage. Nice, that means this locked.
Is it just in this classroom?
No, it's outside the hallway too.
No, we're out. So it must be this entire building. Oh, okay, well, that now unlocked, so that's kind of good. The security system picked up. I don't know what I'm going to do now. Well, let's just take a break and see if the power comes back soon. If not, I guess I'll just have to dismiss early. That's a bummer.
Oh, forgot to finish signing.
Oh, Joey, they're aware of it. I gotta keep can't. That's a bummer. Well, at least we weren't taking a test. I'm not hopeful of the power coming back on. Not hopeful at all. Yeah, I'm just gonna say we're done. Through no fault of ours, of course. No questions on average value, fairly straightforward, at least the setup. Wish I could have gotten through more. As a reminder, the mathematics assignment has been extended to March 4th. Give you an extra weekend to work on it. See you Wednesday.
I'll try to do that, but during the next weekend, probably won't work to do it tomorrow.